Okay, hello everyone. This video I'm going to demonstrate the calculation for the axial loading deformation. Okay, and axial loading deformation, the formula is very simple. We have already, it's very clear demonstrate the formula for the axial deformation in the PowerPoint slide. So I think you can look at yourself. Okay, and we just want to apply this formula to calculate the formation of the axial loaded bar. Okay, and in the example, I'm going to show you that in most of time, we apply sometimes we apply multiple axial loading on a material. Okay, or on a bar. Okay, for example, like this. Okay, there is a bar here, and there is just three external loading here, and it's three extra, or it's more specifically is the three external axial loading on the bar. And the problem wants you to calculate the displacement at the D point, at a D. Okay, and also the displacement of the point B related to C. Okay, that just means calculate the displacement in this section. Okay, so the displacement at D, that means the I would say it's the total deformation of this bar. Okay, displacement. You want to determine the displacement at D. That means the problem wants you to determine the total displacement of the bar, and also determine the displacement at this bar, or deformation of this bar. Okay, here. Okay, BC, B related to C, so that's C. Okay, BC. Okay, so for this problem, and okay, and we have your bar subject to multiple external load. Okay, so we have to use the, okay, I think we mentioned this method a lot. Okay, sorry, we mentioned this method a lot. It's called, we have to use a method called cut section method. Okay, cut section. Sorry. Okay, maybe it's called. We have to use a called cut section method. Okay, cut section method. Cut section method, and we use the cut section method to calculate the displacement, or calculate deformation at each segment, or you can say section. Okay. So when your material is subject to multiple external axial loading, okay, when we use cut section method, determine the deformation at each segment or at each section. For example, we calculate displacement between C and D. For this one, I use the. It's hard to find the subs. Okay, we use this calculate. We calculate D. Okay, DC. Okay, and we calculate a CB, and we calculate a BA. Okay, so that means we calculate the deformation of each section. CD's deformation in CD section, deformation for the BC section, and deformation for the AB section. And then we add this together, that will be the total deformation. And we call it delta D with respect to A. Okay, so this is respect to the point. Okay, so D with respect to C. That means the deformation D with respect to C, and CB means C with respect to B, and BA is B with respect to A. Okay, and then we add this together, we will get a D with respect to A. That's called total deformation. Okay, and do you remember the formula for the calculate deformation? The formula for calculate deformation is NL divided by E times A. N is a normal force, L is a length, Okay, and E is the elastic modulus of material, and A is the cross-section area. Okay, so if we want to calculate the deformation of each section, okay, we need to know the normal force of each section and length of each section and modulus of each section and cross-section area of each section. Okay, that means, okay, we delta DC is equal to, I just use NDC, LDC, and EDC, and ADC. So the same thing, if we calculate CB, we need to know NBC, LBC, EBC, ABC, and delta, final one is BA, we need to know the NAB, LAB, EAB, and AAB. Okay. Okay, so we need to know this lots of information here. And okay, so I'm very lucky. This is the same. This bar is made of the same material as it's called uniform A36 steel bar. So this whole bar is made of only one material. Okay, so that means this the material property is the same in each section because this bar is only made of one material. So the elastic modulus of each section is actually the same. And this problem didn't give you the elastic modulus in this problem description, but they give you the name of the bar. Okay, so I thought in the homework, in your homework PowerPoint homework file, and I have a chart for the elastic property for some steel cut from textbook. Okay, this is the chart. Okay, this is in your homework problem PDF file. And last page, this is the material property in some material. And here, the name of the material in this problem is A36 steel bar. Okay, so let's find A36 steel bar. Okay, here, and the elastic modulus is 200 gigapar. Okay, so the same is 200 gigapar. Okay, it's 200 gigapar. Okay, and this cross section area is constant in each section. Okay, there is no change on cross section. A B B C C D, the cross section area is the same. So A D C equals A B C equal to A B. And it gives you the diameter of the cross section area. So it's pi over 4 d squared. Okay, so it's pi over 4 and the 550 times the power minus square. So what's the value here? Let me see. I didn't calculate the value. Okay, so let's keep it. Okay, let's keep it. Okay. And okay, so what else information we need to know? Okay, we need to know the left is LDC, LBC, and LAB, the length of each section. And this problem is already give you the length of each section, LCD, LBC, and LAB. So we have the information as well. So it's looks very good. Okay, so it looks very good. So let's write down this information. LDC is 1.5. LBC is equal to 1 and LAB is equal to 2. Okay, and the only thing we don't know right now is normal force for DC, normal force for BC section, normal force for AC section. This is the final we don't know. Okay, final part we don't know. So we have to calculate the normal force of each section. And how to do this? How to calculate the normal force of each section? Yeah, to go back to the original, okay, we use cut section method. Yeah, don't forget it's cut section method. It's really used a lot in this course, cut section method. Okay, and then how do we cut a section? Okay, so I just tell you how to cut the section. I cut this here, cut here, and cut here, right? Okay, we do this a lot in this course. So I cut a section here. So that we just use the first section here. First section here, here's D. And we have external loading 70 kilonewton. And this cut section, we have the internal force or internal moment, right? This section will have internal force and internal moment. Yep, and in this problem, we only consider normal force because there is no external shear force or external moment apply on this material. So only have considered normal force only. And you see the picture on the right hand side. This is the solution from the textbook, but I have different. I use a different way to solve. Not a different way. Okay, I use my own way to solve this problem. Okay, so here we have the internal force here. Okay, and internal normal force. I call this internal normal force is NCD, right? Yeah, because it's CD section. So normal force CD. And I assume it's a tension force. I assume it's tension force. And you see here, the textbook just assume it's compression directly. But how do we know it's compression here? Yeah, I really don't have no idea. So I just assume everything is tension. If I don't know the direction of this internal force, I just assume everything is tension. Okay, I assume tension, so it's point to the right. Okay, and okay, and then use a rigid body equilibrium. You don't know rigid body equilibrium? Yeah, don't forget rigid body equilibrium. It's used a lot in this course. So it's pointing to the left, so it's a minus NCD and minus 70 and equal to 0. So what's the NCD is equal to minus 70. So it's kilonewton. Okay, and we initially assume the point to the left, or to point to the left, but we get a negative value. That means the actual direction is point to the right. So actually, it's the same as the textbook. So let's all I want to say is you assume everything's tension. That won't affect your results. Okay, that won't affect your results. So actually, it's point to the right. Okay. Okay, so we have NCD. Okay, it's quick. You keep doing the same thing. We use the same section method to calculate NBC and NAB, and then we have NDC. So NDC, this I call it NCD, but actually they are the same. Okay, okay. So in here, okay, we cut the BC. Okay, BC section. BC is here. So here is C. Here is D is 70, C is 40, and yeah. Okay, we assume here there's the internal normal force, and we call it NBC. Okay, call NBC and assume it's just tensile force point to the left. Okay, and we just use rigid body equilibrium minus NBC plus 40 minus 70 equal to 0. So what's our NBC? Our NBC will be minus 30. Okay, it's kilonewton. I initially assume it's point to the left, but I got a negative value. That means actually it's point to the right. Point to the right. Actually, it's the same as the textbook solution. Okay, the final one, I cut it, the final cut. Okay, the final cut looks like I don't have space here, so I just draw it here. The final cut is here. The final cut is here, so here is, let's say, here is B, here is C, and here's D. So 70, 40, and here is 80. And I assume, yeah, this cut section has an internal force. I call it NAB. It's pointing to the left. So rigid body equilibrium. I don't have any space here, so I write it here. So it's minus NAB plus 80 plus 40 minus 70 equal to 0. So what's our NAB? NAB. So NAB, let's say NAB is equal to 50, right? Kilonewton. And initially, I assume it's point to the left, and I got positive value. That means point to the left. Okay, you see the same as the type from textbook. So my method is kind of different. Assumption is kind of different to the textbook, but we'll finally reach the same conclusion. Okay, so we have the NAB, NBC, and NCD, and then we can solve the deformation as CD section, deformation of BC section, and deformation of AB section. Okay, okay. So I just okay, that's so I just want to put a value in there. So I need the space. So I just erase everything here. I will put a value in there. Okay, and then we'll get the answer. Okay, so formula: normal force times length. Okay, normal force. Normal force here. What's our NCD? Our NCD is minus kilonewton. Okay, we use minus kilonewton. Okay, minus kilonewton and kilo 10 to the power of 3. And times the length. CD is 1.5 length. Okay. And what's the elastic modulus? 200 gigapascal. Don't forget the giga. 10 to the power 9. And what's the cross-section area? Is pi over 4, 50 times 10 to the power minus 3 square. Okay, so this is a deformation of the CD section. And the other part, I think it will be the same. Only difference is the length. Right? And the denominator is all the same. So just write down. You just need the time to use your calculator. Square. Yeah. 50 times 10 power minus 3 square. Okay, what's the normal force BC? Normal force BC is minus 30 times 10 to the power 3. And here is 50. So it's 50 times 10 to the power 3. Okay. Times. Okay, so you just put this information into a calculator and you'll find the deformation of DC, deformation of BC, and deformation of AB. Okay, so what's the value? Okay, what's the value? And right now I just give you the answer. Okay, I just give you the answer directly. Okay, so I think I erased everything here. Just write the answer for you. Yeah, do the practice by yourself. Yeah, especially do some practice using the calculators. Yeah, it's not easy to get the right answer even if you use a calculator. So let me see. I think this delta DC is equal to, I think here is minus 2.675 times 10 to the power minus 4. And it's meter. The unit is meter. Unit is meter. Okay, you can translate to the millimeter. Okay, it's all right. It's all right. And the BC or CB. What's the CB? Okay, it's minus 7.643 10 to the power minus 5. And the unit is also meter. And the final one is AB, right? AB. So it's 2.55 times 10 to the power minus 4 in the meter. And the negative value just means the compression. The positive value just means extension or tensile. Okay, so this is the deformation of each section, and then your delta total is just add these three together. You just mentioned this before. You add these three together, your total deformation. The total is 7.634 times 10 to the power minus 5. It's meter. Okay, so that's the axial loading. And when the bar is subject to the multiple axial loading, yeah, you use the cut section method. Yeah, don't forget cut section method. Calculate the normal force, internal normal force of each section, and then use the formula. Yeah, I erased the formula, sorry. And use the formula, deformation formula. Okay, NL divided by EA. And to calculate the deformation of each section. Okay, and add them together, that's a total deformation. A total deformation when the bar is subject to this external axial loading. Okay, so don't forget cut section method, and then don't forget ridge body equilibrium. This is doing all the time in this course. Okay, so I just stop video here, and I will do another demonstration on axial loading problem. So I'll start the video here and see you in another video. Bye bye. Right? Here.